Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, Module 8, Part 2, NeuralProphet. This is going to be the very last theory lecture of the entire deep forecasting course, and we're going to end with this powerful model called NeuralProphet, which is an extension to Prophet model and is a good combination of whatever we learned in Module 3 and 4 and bunch of the Module 6. So it's a combination of econometrics and deep learning models. So this is going to be an exciting one. In the previous theory lecture, we talked about the original Prophet model. We read the paper together, which was forecasting at scale, and that researchers at Facebook wrote it back in 2017. And we talked about intuition, the mathematics, and the Python implementation in very detail. So make sure you check out that video and then jump into this one because we need that background to make sure we understand all the theory behind the NeuralProphet. In this one, we're going to talk about another paper, which was an extension to the Prophet model and was published back in 2021. The name of the paper is NeuralProphet, Explainable Forecasting at a Scale. So exactly the same way that I broke down and demystified the forecasting at a scale paper last time, we're going to read this paper, the NeuralProphet, together, and I'll make sure that I go over the intuition, mathematics, and also the Python implementation of NeuralProphet as well. So at a high level, we know what's the difference between Prophet and NeuralProphet. Prophet covers trend and seasonality and holiday effects and add them in a linear fashion. However, the NeuralProphet is going to add the lag values to that to capture short-term dependencies better. So we have that autoregression part, and we can add those autoregression parts either in a linear way or a neural network nonlinear way. So that's at a very high level what is the difference between the two and what are the prereqs for this video. All right, so let's jump into what was the strength and weaknesses of the Prophet model and why we should go beyond that. So let me quickly remind you what is Facebook Prophet. You have seen this slide before. Actually, if you remember in the very first session of the course, we talked about time series decomposition and how we can model those components and then add them together. So Facebook Prophet is nothing fancy. Actually, it's borrowing that idea and it's talking about how we can come up and model these different components. So it has three different components. One of them is trend. So this was the trend component. This was the seasonality component. So seasonality. And this last one was the holiday effect, right? And then we ended up putting these things together linearly. So we call it the additive model. And then the rest was idiosyncratic noise, right? Whatever we were not able to capture through these different components. So we add them together and we come up with some prediction. We call it these are our forecasts, right? So, and also in Facebook Prophet, the authors talked about scale. So this is the title of the paper, Forecasting at Scale. And we said they had three things in mind when they were talking about scale. So first thing, it's the model is accessible. By scale means large number of people can make these forecasts, right? The second one was large variety of forecasting problem can be covered by Prophet, which I guess that so they were not successful in their second objective because we will see that not large variety of forecasts is able to be done with Prophet because it has its own caveats. We're going to talk about the limitations, and hopefully NeuralProphet is going to kind of fix those limitations. And then the third thing they meant by scale was large number of forecasts. So we could run multiple of these forecasts in parallel and then basically do forecasting at large scale. So this is what they had in mind. Now, the authors of the NeuralProphet have the exact same idea of scale in their mind, and they are going to add this notion of autoregression to that to make sure that it's also relevant for a large variety of forecasting problems. So it's going to overcome the caveats of Prophet. So that's a quick reminder of what was Facebook Prophet. So let's look into the strength next. Okay, so what are the strengths of Prophet model? The first one, which in my opinion is the most important one, is this notion of analyst in the loop. As I said earlier, Prophet is supposed to be accessible for analysts with minimal statistical background, right? The reason is that there, if you remember from the previous theory lecture, there is this three knobs that we talk about. So the analyst can basically tune these knobs. One of them was number of change points to play around with the trend component. The other one was the magnitude of seasonality, and the last one was the magnitude of your holiday effect. So even with the zero or minimal statistical background, the analyst could play around with these things and leverage their domain expertise to make sure they can promote better and more personalized forecasts. So this was one of the bigger seller of profit model. So anybody at large scale with some domain expertise could use their knowledge and basically use Facebook Profit for doing business time series forecasting. The second one, this is a flexible additive model, right? So as I said earlier, it's going to combine trend, multiple seasonality. So that was key. We talked about this multiple seasonality last time. Not all the econometric models that we covered in module 3 and 4, they could handle multiple seasonality. They at best, they could do just one type of seasonality, but Facebook Profit, as we discussed in the previous theory lecture, it can handle multiple seasonalities. And of course, it's going to add those holiday effects to these trends and seasonalities in a simple additive framework. So again, the structure of the model is pretty straightforward, and we can add and remove components as we see fit to our data. And then the next one was the automatic adaptation. So because it's going to do, so for example, imagine we have a time series like this, right? There are some regime changes here and there. And then if we play around with this first knob, which was the trend component, and then without even specifying the number of change points, there's a parameter that we can play around with that one. And it's going to automatically capture how many change points do we need. So maybe in this one, we need 2, right? So there's 1, 2, 3. So it's going to break it down into this piecewise linear components, right? So so that's the automatic adaptation part of the Facebook Profit model. So it's going to be robust and capture those sudden shifts in trends and seasonality without manual intervention. And lastly, as we said last time, this Facebook Profit is resilient to data issues, specifically missing values, right? Because there is no lag component in the Facebook Profit model. So this is both good and bad. So you're going to see this non-recursive in the limitations as well. But what is the plus side of non-recursive structure of Facebook Profit is that there is no lag value. So this means that we can easily go ahead, and if there's any missing data, we can just ignore them because the different components are not depending on the previous observation. So if there's one missing value, we can just move on to the next one. So this is going to be a big advantage of using Facebook Profit if your data set has lots of missing information. This non-recursive structure also has another big advantage, and that is, we didn't talk about it specifically last time because I wanted us to learn NeuralProphet and then talk about it, but let's discuss it. So because this is non-recursive and we have 3 components, right? We have this trend, seasonality, and let's say holiday component, right? And then all these components are only, when we are doing forecasts, they depend on some time step. So if you're in time step 1, time step 5, time step 10, when you're forecasting into the future, you just simply need to replace this T with those numbers, right? The same story for seasonality and holiday effect. So this means that with Facebook Profit, we can do multi-output. So multi-output forecasting. So if you remember, we had 3 types of forecasting, right? One was one step ahead, which was single output. So the single output, we could have one step ahead, or we could have multi-step ahead. So multi-step ahead was basically putting a bunch of these one step ahead in a for loop and then predict into the future. And we said that not all the econometric models are able to do multi-output forecasting, right? Because that was not feasible. We couldn't do it with ETS or ARIMA. However, with Facebook Profit, because we have this non-recursive design, so we can be able to do multi-output at the same time. So for example, I have a time series with 100 observations in the past, and now I want to make a prediction for the next 12. So we can do it at one step right now for all the 12 steps into the future. So this is one of the bigger advantage of NeuralProphet compared to our econometric models. So we talked about machine learning models as well. So not all the machine learning models could do that, but some of them, like the decision tree based models that we could have multiple output at the same time, were able to handle this. And of course, the neural network was also able to do multi-output. So I just want you to be aware of this subtle point when it comes to forecasting horizon, that Facebook Prophet is able to do multi-output forecasting at the same time. So this was one of the bigger advantages of Facebook Prophet as well, which comes with this non-recursive design structure. Okay, so these were the strength of Prophet, which made it famous back in 2017, and so many practitioners used it, and they're still using it. But I think, in my opinion, with the NeuralProphet that we have as of 2021 onward until today, I think there is no reason to use Facebook Prophet anymore, because the NeuralProphet is actually more powerful. And if you read the paper, they have tested against different benchmarks and compared to Prophet. And almost always NeuralProphet is outperforming the Facebook Prophet. So, but we needed to know the structure of Prophet, because NeuralProphet is simply an extension to that. So let's talk about the limitations of Prophet, and then you're going to see clearly why we should go beyond Prophet. Okay, so what are the limitations? The biggest one is this one, right? So lacks local context. It cannot learn short-term autoregressive patterns simply because we are not using any lag terms. So that's the biggest caveat of Prophet, in my opinion, because remember, in order to capture the short-term dependencies, at least lag 1 typically is the most important factor that you can think of. So remember, in stock price prediction what we had. So, and if you remember, we talked about the benchmarks sometime at the beginning of the course. One of them was the naive forecaster, right? So what was the naive forecaster? Your prediction is, y hat t plus 1 is equal to your yt, right? So whatever happens today is your best predictor for tomorrow, right? Well, of course, with some errors, and then sometimes a constant. It's a random walk with drift or no drift, but to just simply say whatever happens today matters a lot for predicting tomorrow. And we said that for stock price, for example, many econometric or machine learning or even deep learning models were having hard time to just outperform the naive forecaster, simply because lag 1 was super important. And later on in the Python section of the NeuralProphet, I'm going to show it to you that when you're using Prophet or NeuralProphet, or even NeuralProphet without AR components, without any lags, they cannot simply outbid your naive forecaster when it comes to stock price. But as soon as we add this lag components and we twist and tweak it a little bit, it's able to outperform the naive forecaster when it comes to stock price prediction. And that's true for many business time series out there. We know that we need to look at the local context, basically what is the short-term impact, what is the temporal impact of your time series over time, right? So this is the biggest limitation of Prophet, and that's why Facebook Prophet, the NeuralProphet, has almost replaced Prophet completely, right? So that's the biggest one. The second one is technically it's challenging to extend, because we talked about it last time that Facebook Prophet is built on Stan, and Stan is a probabilistic programming language, right? So it means that it models problems using probability distribution instead of using traditional loss functions. In Prophet, the core modelings had two things, right? What is the likelihood function, and we need a bunch of priors over model preferences, right? Or model parameters. And then we did this maximizing a priority, just like maximum likelihood estimation. It was maximizing the posterior probability to find the value for the parameters of the model, right? So this simply means that we cannot use any kind of custom loss function we want for with NeuralProphet, with Facebook Prophet, right? So we have to go with whatever the API offers, unless you are comfortable with coding in Stan, and then you can play around with those things yourself. So, and you're going to see later that NeuralProphet is built on PyTorch, which is heavily used for super easy customization in with any kind of deep learning architecture. So that's one of the bigger advantage of NeuralProphet over Prophet. And then lastly, we assume additivity, right? We said that there are different components and we're going to add these components in a linear fashion. But what if they're not linear? I know, some sort of simple multiplicativity is also available through Prophet, especially for seasonality component. We could add it in a multiplicative way, but it doesn't go beyond that. So what if you want to add these components in a complete nonlinear fashion, right? So what if you wanted to use a neural network to just add these components together? So this is something that Facebook Prophet is missing. And that's why NeuralProphet became a thing, after 3-4 years after the Facebook Prophet, because it kind of fixed all these caveats. And we're going to talk about this additive component. It is still adding the trend and seasonality and events in a linear fashion, but when it comes to including the lag components, we can now use neural networks to capture those complex relationship in the lag values. All right, so now let's go to the core of NeuralProphet. Let's open the paper together and then break it down and try to demystify it. So with this background, let's do Module 8, Part 2, NeuralProphet. Okay, NeuralProphet, Model Intuition. So what is NeuralProphet? So here's the link to the paper. I highly encourage you to have it open, just scan through it, and then make sure you're following along, okay? So just like Facebook Prophet, the NeuralProphet is designed for industrial time series. So what are industrial time series? I mean, something like demand forecasting, supply chain management, budget allocation, infrastructure planning, and you name it, right? And again, just like Facebook Prophet, the NeuralProphet is explainable because obviously it has this decomposition-based structure in it. It's a scalable, it requires minimal tuning. So this has this notion of analyst in the loop thing, right? And then it's reasonably accurate. So right off the bat, this NeuralProphet model is reasonably accurate. And we're going to see with a little bit of tuning, it can outperform many traditional and machine learning and deep learning models. So that's why we're excited about this. And it's a hybrid forecasting framework. So it's going to combine our classical, traditional econometric and decomposition-based time series forecasting models with the more flexible and advanced neural networks. So that's why we call it the hybrid approach. And that's why we're teaching it at the very end of this course, because you're already familiar with all those concepts. And this is important. NeuralProphet is based on PyTorch. It's open source and customizable. So this is a big deal because we know that with PyTorch, we can update, this NeuralProphet, your model basically can be customizable. It can be updated with the latest innovations in deep learning. You can play around with the loss functions, learning rate, stochastic gradient descent, whatever, or any kind of a stochastic gradient descent based algorithm you want, you can use with PyTorch, right? So this is very different from Stan, which was limited when it comes to the optimization and solving for the parameters. So with that, your NeuralProphet is going to be able to add power and flexibility to your time series forecasting through capturing the local context, which is introduced by adding that AutoRegressive components and also some covariates modules. So these are some extra regressors, right? So these are some lag values, yt minus 1, yt minus 2, etc. And these are some other extra regressors that you can add them themselves or the lag values of those ones, right? And these extra regressors can be modeled both in a linear fashion as a linear regression or neural network. So this is what makes it super exciting, because you have those covariates. With our machine learning, we could add those covariates, right? And then here as well, we can add these covariates along with the autoregressions, and then we can add them in a nonlinear complex fashion. So with the hope that it can capture those nonlinear patterns. All right, so what are the model components of NeuralProphet? So here, I directly borrowed it from the paper. So this is the formula for the forecasting equation, right? So we have 1, 2, 3, 4, 5, 6 components, right? The first one is trend component. So this is analogous to our G components in the Facebook Prophet. So let me actually write Prophet. So for Prophet, we had something like this, y hat is equal to. And then the seasonal component is pretty much the same. And then we used to have H of T. Now we just use the letter E for events, right? So we have trend, seasonality, events, and now these 3 new components. So these are new, and let's look at them one by one. FT, these are some exogenous variables, and F stands for future. So again, for whatever reasons, they wanted to call it F. So these are the variables that we know the future, past and the future value of those variables, right? So for example, we're doing some demand forecasting, right? And then you have a variable like temperature. Imagine the granularity of the data is daily, and you have a good prediction of the temperature for the next month, right? So we say that, okay, that temperature is available historically and into the future. So I can use that temperature as one of the exogenous variables for my demand forecasting, right? So that's one thing. The other one is L. This is also exogenous variables, but these are sort of exogenous variables that we don't know the future value. We only have the historical data, so that's why we're going to use the lag observations of those, right? So for example, again, in our demand forecasting thing, I can think of, we are trying to predict the demand of a product and you have its historical price, right? So you don't know what is the price of that product into the future, but you know what is the price historically. So you can use lag prices to include it in the model to do demand forecasting for the future, right? And then finally, we have this AutoRegressive component. Sometimes we show it with AR. See, so this is the big deal. So this is actually when you're adding your lag values here, yt minus 1, yt minus 2, and etc., right? And as I said, you can add these in a linear way, or you can add it through neural network. So these are the model components. And in the future slides, we are going to look at them one by one and see how we can put them together and call this model NeuralProphet. Before I go there, I just want to highlight a very important point here. All these modules, let's call these components modules, right? So all these modules must produce H outputs at the same time. So this will allow your NeuralProphet to be just like the Facebook Prophet, a multi-output forecasting model, right? So this means that if I have a trend component and if my forecasting horizon, let's say, is 12, the trend component should be able to generate those 12 predictions into the future at the same time. The same goes with seasonal components, event components, F, A, and L, right? So for the first 3, this is pretty straightforward. This is exactly the same as Facebook Prophet, so we know that it already can generate multi-output at the same time. But how can we, especially when we have lag terms, how can we produce multiple output at the same time? So yeah, here's it. Hint, we have to use the neural network version of that. That neural network can generate multiple output. If you want to do the linear version of adding these, let's say, lag terms together with bunch of coefficients, let's say, then you have to basically train the model H times, into the future, right? If your H is 12, you have to literally train these 12 times to make a prediction for different H forecasting horizons into the future. But if you use a neural network architecture, so it's going to generate all those outputs at the same time. So I assume you have watched the previous theoretical lectures in this course and you're following along. If not, that's totally fine. And this is not something that many time series textbooks discuss, but I think this is very important for you to know what time series models are able to do multi-output forecasting, what time series models are not. So NeuralProphet is one of those models that can generate multi-output at the same time, and we're going to look into the details. All right, so starting with the trend component, this is pretty much similar to what we discussed when we were reading the Facebook Prophet paper. So trend is modeled as a continuous piecewise linear series. So what does that mean? Look at this time series, for example, and ex post we have 12 change points. So we call them NC change points. So in this case, 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And as you can see, there's a separate slope for each of these series, right? That's the whole idea, right? We can break it down into multiple change points and figure out the slope and an offset parameter for each section, right? So, and as I said, there's for each section, for each of these series, there's a time-dependent growth rate. We show it with rho, and an offset parameter. We show it with delta, right? So this is nothing fancy. We're just saying that wherever you are. So for example, we are here. There is a growth rate. We show it with this row. So for example, this row 1, it's negative, I don't know, minus point. I'm just speculating 0.3, right? So that's your row, right? And then there's a delta 1 and all the way to delta 12 in this case, and row 12. Delta just makes sure, this is the offset parameter, just to make sure the continuity, right? So for example, if you're in this region, and this is the slope, you have to make sure that it adds to the next one, right? So there's this continuity. So delta guarantee that continuity, and rho is just basically your simplest slope, which is constant between those change points. And then what is gamma? Gamma is simply, and we can think of it as binary vector, which represents whether the time t is past each let's say change point, right? So for example, again, this is pretty straightforward. We just want to make sure that if we are here, well, that's the last one. If we are here, and then we are not basically looking to the previous growth rate, so we are only looking into this one, right? So that's the binary a binary vector representing if time is past each change point. So we show it with something like this, right? And then, so the only difference between this one, the NeuralProphet trend component, and the Prophet trend component is that NeuralProphet does not allow for nonlinear saturating trend. So if you remember the Facebook Prophet, we had two types of trend modeling. One was using this nonlinear saturating trend. So the idea was that we have a saturating time series, either increasing or decreasing, right? So with NeuralProphet, we don't have that luxury. We just look at it as piecewise linear series, right? Okay, and here's the formula. So again, this is a formula of forecasting the trend component, and this is a breakdown of the trend component. So we start from some initial, basically this is your initial offset parameters. Think of it as initial intersect. And then we are multiplying these gammas to the slopes and multiply it by t, right? So, and then this is going to, so this is going to be your, let's say, initial. So for example, we are here, starting point, and then adding some, obviously, some growth rate to that as well to capture the trend component. So this was the trend. It's pretty much similar to Facebook Prophet with this difference. Just keep that in mind. Okay, so the second component is S, seasonality, right? So we're talking about this one. Again, just like the Prophet model, we're going to use Fourier terms to basically define each seasonality. So here's a formula for that. And if you remember, we talked about it in the previous theory lecture when we covered the Facebook Prophet. We talked about Fourier series, right? It's a combination of sine and cosine, right? So here you're going to see the sine is in red and cosine is in green, and you can basically mimic any kind of regular seasonal component by combining these sine and cosine, right? And the cool thing is that if we use more number of Fourier terms, it will allow for more complex and multiple seasonality, right? And this is pretty straightforward. So what we're doing here is that we're saying at the end of the day, I have something like this. For example, A1 cosine something plus B1 sine something, right? And then I can add another seasonality. So for example, for this one, seasonality period is 1 for daily seasonality. I can use, you can plug P is equal to 1 here and simply just use a formula. I can then say P is equal to 7. I have A2 cosine, again, that thing, plus B2 sine, that thing. So this is weekly data. We can do P is equal to, for example, 30.5 for monthly data. We can do P is equal to 365 point, let's say 25 for yearly data, right? And the cool thing is that this is what makes the seasonality components, in my opinion, more exciting compared to our ETS models, the econometrics models, and that we covered at the beginning of the semester, right? So simply because we couldn't do something like this with an ETS, 30 point something or 365.25. But with using Fourier terms, we can obviously do that, right? So, and then another thing is that we can add these multiple seasonality in an additive way, so simply add them together and call it the seasonal components, or a multiplicative way. So multiplicative, simply we're saying that if this seasonality is multiplicative, just multiply it by the trend component, right? And in Python, we're going to see that this framework is automatically activated for daily, weekly, and yearly, depending on the data frequency. So if you have, for example, hourly data for, I don't know, 4 or 5 years, you can easily look at the daily, weekly, and yearly are going to be automatically activated. If you have daily data, obviously only the weekly and yearly are going to be automatically activated. All right, so that was the second component, seasonality. All right, the next component is AutoRegressive. So I'm going with the order that the components are presented in the paper. So that's why we jumped from trend seasonality to AR or to AutoRegressive component. So in my opinion, this is what makes NeuralProphet exciting. This is what makes it a preferred model compared to Facebook Prophet. And there's nothing new here. You have seen this before. And we start with our classical ARP process model, right? So this is what we covered in our module 4 ARIMA models, right? So this is a formula for a simple ARP process, right? Nothing fancy. YT is equal to some constant plus what are we using here? Theta, yeah. Theta 1, YT minus 1 plus theta 2, YT minus 2 plus all the way to theta P, YT minus P plus some error, epsilon or E, whatever. Okay. And so this is the AR process. There's nothing new here. We have seen before. And what makes NeuralProphet interesting is that it says, you know what, you can add these components both in a linear way like this, or add it in a neural network way. So this is the modified version of the ARNet model, which was proposed in 2019. So basically NeuralProphet is just mixing the two, says that, okay, let's add these components, YT minus 1, YT minus 2, YT minus 3, and etc. We can simply add it in a linear model, or you can think of having it as a deep learning model, a neural network model. So let me actually show you the network. So we have seen this before, I think in our module 6. So imagine we have 3 lag terms. You can pass it to a neural network with different number of hidden layers. Let's say this is hidden layer number 1 with, I don't know, I'm just speculating, with 5 or 6 neurons. And then I have another hidden layer. I can have another hidden layer, right? And at the end of the day, I can have my output, y hat t, right? So of course, these are all connected. So this is how your network is going to look like. And at the end of the day, so you're going to make a prediction for this y hat t, right? And this, obviously, you can sparsify the model weights by some sort of regularization. Either you're using, let's say, a linear model or a neural network model. So what I mean by that, again, nothing fancy here. Imagine I can use 50 lags, right, in a linear model, so something like this, and say, you know what, let's use some sort of L1 norm, absolute value. L1 norm, the penalty, add it to the loss function, and then regularize those weights. So for example, at the end of the day, your theta 1 is going to become a big and large number, and your theta, I don't know, theta 15 is going to become irrelevant. So we're going to set those things close to 0, right, or exactly equal to 0. So this is sparsifying your parameters. The same story with your neural network. We know that we can use regularization to just play around with the weights and the importance of each of these lag variables. And one last important thing is this bullet point. So the AR component is, if we do it in a neural network fashion, it's able to produce multi-output, this age forecast, with one model. How do we do that? I want you to pause the video and think about it. from module 6, how did we do multiple output with neural networks? Yeah, we can simply add those ones to the last layer, y hat t plus 1, y hat t plus 2, all the way to y hat t plus h horizons, right? So simply we can expand it to multi-output forecasting. So this is the biggest advantage of having a neural network architecture. If I wanted to go with this, if I have h horizons, let's say if I have 12 horizons, this means that I have to just run the model 12 times if it was linear, okay? To predict y hat t plus 1 first, and then separate run of the model for y hat t plus 2, and etc. But with the neural network version, we can do it all at once. So hopefully this is clear. So this is very subtle that if you're reading the paper, it's hard to follow what is exactly happening and why this NeuralProphet model is able to make just all those forecasts at the same time. So we already talked about the trend component can do it, seasonal component can do it, and now we know that this AR component can generate multi-output at the same time. And as we go through the rest of the components, you will see that that's the case for other components, and this means that your NeuralProphet is able to do multi-output forecasting too. Okay, so the next component is our lagged regressor. So lagged regressors are basically used to correlate other variables to our target variable. And as we said earlier, at the time of forecasting, the future of these regressors is unknown. And we don't need to know that because when we're doing H step ahead forecasting, we're going to use the historical data and make those predictions at the same time for the future H steps. So we don't need to know the future value of these lag regressors. And each of these lag regressors are basically an ARP model, right? So this is, we can have, let's say our regressor is X, so we are going to add X t minus 1, t minus 2, all the way to t minus p. So this is our ARP model like that, right? It's not autoregressive because we're not using the target variable, but this is a lag variable of a new feature X, okay? And again, as I said earlier, each module, so here this is L, it's producing H additive components to the overall forecast. So basically it means that if you're doing, for example, your forecast horizon H is equal to 12, when for each step from 1 all the way to 12, we're going to get a separate number for this component, and we're going to add it to the other components to come up with a prediction for h is equal to 1, h is equal to 2, all the way to h is equal to 12. And obviously, like the autoregressive part, so we can simply, add it in a neural network version as well. Okay, so this was the lagged regressor. The next two components are our FT and ET. So this is the future regressors, and these are the events. They're pretty much similar, and actually you're going to see that the next slide is pretty much the same as this one. So let's do them. So these are the features that both past and future values are known at the time of making forecasts, right? So as I said earlier, you can think of it as, if you want to think of an example, it can be like demand forecasting, and you're thinking of a temperature as a variable that you know the future values as well with a good accuracy. So you can add that to your demand forecasting problem, right? And we can have a bunch of those things, and the effect of all those regressors are going to be added to your forecasting as this capital F of t. So, and I think, this is, for example, for one of those features, right? So this notation is not the most straightforward one because typically we reserve f as a function, but simply here we mean that this is just a regressor, right? This is a regressor x that basically its value historically and into the future. So the difference between f and l in the previous slide is simply that, we know the value of these things into the future. And these are simply, you can think of it as betas, right? We have to remember there's a coefficient for your x, so this is basically what we're talking about, right? So this is these small letter df, these are the coefficients for your exogenous random variables that we know their values historically and into the future. And then obviously we can add them in an additive way like this. So this is the overall impact of those features, which we can add it to the forecasting model, or we can think of it as a multiplicative. So if it is multiplicative, we need to multiply it by the trend component and then add this whole thing to the forecasting equation. So the next one, which is the event, is pretty much the same. So let's look into that one. Okay, so the last component is going to be our events. No, we show it with E, and we know that these events or holidays can happen sporadically during our time series horizon, right? So this is the NeuralProphet, just like Facebook Prophet, it allows for modeling two types of events. The first one is user defined. So for example, I don't know, you are a drugstore, you have some promotions, and then you can add it in different sporadic time steps, and you can add it to the model, or it can be country specific holidays, right? So just again, just like Facebook Prophet, the NeuralProphet can handle those two types of events. And the events are modeled like what we did for F. So basically, just like the future regressors, we know the future value and the historical value of these events. So basically, these are some binary variables, right? Now, for example, if it is Christmas or calendar, US calendar, you know it into the perpetuity, right? And so that's why we're going to treat it just like future values. And the effect of all those events, so we can combine a bunch of those things, right? You know, your custom calendar, your US holidays, different, for example, China holiday, different countries' holidays, you can add them on top of each other and then put it in a vector called ET, right? So we can add them in an additive manner. If it is additive, we just simply use sum, or if it is multiplicative, we're going to multiply it by trend, right? And again, just like F, we're going to look at these events. This is a binary vector, and this is their coefficient. Again, it's not the best letter that the authors could use, but typically we use Greek letters for these coefficients. This small letter z, this is just something like theta or beta or whatever. These are simple coefficients for those events, which are binary effects. All right, so, and one last thing before we move forward. Again, just like the Facebook Prophet model, we can add a couple of days or more before and after events as well. So for example, you have Black Friday and you want to see what a day before Black Friday and a day after Black Friday. You want to add those impacts to your forecasting model as well. So you can simply do that. And we're going to see next time in Python how we're able to play around with all these hyperparameters. Okay, now that we know all the components of the NeuralProphet model, let's talk about pre-processing, training, and post-processing of the NeuralProphet model. So feel free to read the paper, but I'm trying to summarize everything you need to know from the paper here on this slide, so just bear with me. Let's start with the pre-processing. So obviously, the missing data is going to be a big deal in NeuralProphet. We said that in Facebook Prophet, it wasn't an issue because that model has non-recursive design, the Prophet itself. But NeuralProphet, because it has AR components, AutoRegressive components, then the missing values are going to be problematic. So for example, you have, I don't know, you have 12 lags. You have something like this. You go yt-1 all the way to yt-12. And imagine your forecasting horizon is just 4. So you want to forecast 4 times into the future. So at each observations, you're seeing yt-1 all the way to yt-12 and then yt. So here you're predicting yt plus 1, yt plus 2, and yt plus 3, right? So if there is one missing observations, then you have to go ahead and drop 16 observations. Right? Because that observation, that let's say whatever that number is, it's going to show up 16 times, right? Because you have 12 lags and then 4 forecasting time horizon to forecast into the future. So you need to drop 16 observations for each missing value, so which is going to be very problematic. So what is the solution? The solution is just to impute this, right? So that's why we need to do some imputation when it comes to NeuralProphet. And the way that the default imputation works for NeuralProphet is actually, I'm going to show it to you. It's basically heuristic, but you can play around with all those parameters and tune it yourself if you wish. So imagine this is your time series. You go up and down, and then there are a bunch of missing values here, a bunch of missing values here, and etc. Right? So if it is less than 5 missing values, either going to the left or right, so we're going to do simple linear interpolation. So it's going to be something like this. And where's that number 5 is coming from? It's not a magic number. This is what not the number that authors use it, right? So if it is 5 missing observations or less than that, we're going to do simple linear interpolation. Okay. If it is more than 5 and less than 20, again, where's that 20 coming from? This is subjective. They're going to use a rolling window, right? So basically, they're going to use rolling average window size 30. So whatever it is, so it's going to use the past 30 observations. You report a rolling average, and then when we come to this part, which is a missing value, we're going to use those rolling moving averages, right? And replace them with that, right? And so this is going to work when we have 20 consecutive missing observations. And the authors say that if it is more than 20, then the imputation algorithm is going to stop. So either basically we're going to say that, okay, we're not able to make a prediction because there are too many missing values. And because this is a recursive model, we need those things to move forward. And of course, you can tune all these parameters and hyperparameters using the NeuralProphet API. All right, the next thing in terms of pre-processing is data normalization. I think there are different options you can choose. You can do min-max, you can just switch it off, you can use a standardization or a combination somewhere between min-max and standardization. We can do softmax. And yeah, you just check out the paper. It's pretty straightforward when it comes to data normalization. And lastly, for pre-processing, we have to tabularize the data, because again, it's using PyTorch and it's using a stochastic gradient descent for optimization. And for any kind of a stochastic gradient descent based training, we have to basically tabularize the data. So we have to sort it in a nice rows and columns, right? Yeah, that was the pre-processing part. The next one is training. Okay, when it comes to training, NeuralProphet is fundamentally different from Prophet here, simply because we're using PyTorch and we can do any kind of mini batch stochastic gradient descent fitting, right? And that thing is going to be compatible with the vast majority of all the deep learning methods that we know. So for example, if there's a new deep learning model coming out, which is based on a stochastic gradient descent fitting, we can use it and apply it to our NeuralProphet. Remember, that was not the case for Facebook Prophet, because Facebook Prophet was using a STAN, which is a probabilistic programming language, and is not able to work with this kind of flexible loss functions and things like that, right? So yeah, that's the training part. As I said, because we're using a stochastic gradient descent based thing, we can play around with any kind of loss function that we can think of. But by default, the authors are using the Huber loss function, which is a combination of mean squared error and mean absolute error. So for the larger values, to just make sure that they're not penalizing the outliers, or it's less sensitive to bigger errors, right? So this is called Huber loss function, but you can replace it with any other loss function that you can think of. When it comes to regularization, it's going to, again, by default, it's going to use a log transformed version of L1, and it's going to add that to your loss function and then do backpropagate through time. So that's a straightforward. Then when it comes to optimizer, it's going to be any kind of atoms or momentum-based optimizers, learning rate, batch sizes, and training epochs. So the authors are using some heuristics. So we're not going to touch those default values when it comes to the Python implementation part. But again, these are some of those parameters that users can change them if they wish. And finally, the paper talks about post-processing. So obviously, we need to transform back the normalized value into their initial distribution. So this is a transforming back, which NeuralProphet is going to do it automatically. When it comes to metrics, they're going to report and record root mean squared error, and I think mean absolute error by default. But obviously, you can specify your own metrics and add it. And when it comes to forecast presentation, they will give you a detailed breakdown of the forecast. So for example, remember we have 6 components, right? It's going to say, so this is your y hat, whatever it is, and you're going to see the trend component. It has a value, seasonal components, event components, lag values, future values, and then AutoRegressive components. So there's a number for each of them, and then you can go ahead and add them together to get your forecast. So this is when it comes to the thing that they say, hey, this NeuralProphet is explainable, so we can clearly break it down into its components. So it is really explainable unless you are using a deep neural network when it comes to this AR components. And then you're trading off between explainability for that AR component and accuracy. Of course, if you use a bunch of neural networks to add those lag values together, then it might be more accurate because it's more flexible and it can capture complex patterns in short term better, but it comes at a cost that it's less explainable. But all the other components are pretty straightforward to interpret them. All right, now I want to take some time and talk about this multi-step forecasting when we're using Preprocessing versus NeuralProphet. Because in both of the papers, I noticed that the authors are not specifically talking about these things. And I just wanted to make sure that you're following what's going on with that, right? So let's start with Preprocessing. So Preprocessing predicts multiple future points in one go using calendar-based components like trend, seasonality, and holiday, right? Remember, when we were modeling the Preprocessing model, we said that the trend component, whatever it is, well, we use the letter G. It's a function of time itself, and it was not dependent on the previous lag variables or things like that. The same story was true for S or for holidays, right? I think for holidays we use letter H in the Preprocessing model. So we were able to do multi-output forecasts. Let's say your forecasting horizon is 12, right? You can use Preprocessing and then make all those predictions at the same time because, again, there's no lag values. We're not using previous. The model is non-recursive, so we can do that. So forecasting style is going to be direct. It's not going to use past the lag values of the target variable, so that's what it is. And the forecast is going to be independent. So at each forecasting horizon, for example, H is equal to 1, 2, 3, whatever it is. So we can do it at one step. And because of that, there is no error accumulation. So if you're doing multi-step forecasting to the future, if I'm at a step 5, I don't need the value from step 4. Or if I'm a step 4, I don't need the value from step 3. We're going to, whatever it is, we're going to do it all at one step. So that's a big advantage. But the disadvantage of Preprocessing was that because it's not using those recursive modeling, it was not able to capture the short-term dependencies. NeuralProphet wanted to fix that, and actually is able to fix that, but we need to be very careful if we are adding those lagged values of the target variable in a linear way or in a neural network. So starting with neural network. So NeuralProphet is going to use the past lag values, and if configured with neural network, just something like ARNet, it can predict multiple outputs at the same time directly, right? So this is pretty much the same as the capability as what Preprocessing could do, right? So because remember, guys, we have a bunch of lag values, yt minus 1, yt minus 2, etc. We pass it to a network, whatever it is, and then we said, let's say have 3 outputs. Let's have 12 outputs for h is equal to 12, right? So if that's the case, we're going to do a direct forecasting for the 12 horizons, and it is using the past values, and your forecasting is going to be independent over different time horizons, and there's no error accumulation. However, if you're using NeuralProphet, and if you're using linear combination of these lags, right? So if you're using, for example, ARP version of that, adding them linearly, right? Like theta 1, yt minus 1 plus theta 2, yt minus 2, whatever. If you're doing it that way, then your forecasting style is recursive. And because it is recursive, it means that forecast of tomorrow depends on today. The day after tomorrow depends on tomorrow, and etc., etc. So that means that we can come up with this error accumulation, right? So which is not a good thing. So you have to just be aware that that's what it is when you're using NeuralProphet, and basically you're adding those lag components in a linear way. And this is the default setup for NeuralProphet. So later on, when you're doing, for example, Python, if you're building your model and say, hey, this is the model and it's simply neural NeuralProphet, whatever it is, open close parenthesis. If you leave it like this, then right off the bat, your NeuralProphet is using the linear version of the AR components, not the nonlinear. And if you do that, and if your forecasting horizon is long, let's say 30, just be aware of this danger of error accumulation. So this is a very, very subtle point that, again, the authors in both papers, I didn't see that they explained it clearly, so hopefully it is clear now what is the default value of the parameters in either of these models is doing when it comes to multi-step forecasting. Okay, so I think now you know everything you were supposed to know about NeuralProphet. You know all the components, you know all the details when it comes to forecasting multi-horizons into the future, and I think you know all the details. And if you combine this with the previous theory lecture that I covered, the Facebook Prophet, now it's time to just sit back and compare the performance of the two models on different data sets. So the way that the author are going to do it is basically benchmarking two sets of data sets. One is synthetic data, and the other one is bunch of real world data sets, including our airline passengers and a bunch of other famous time series data sets. So the reason that they wanted to use synthetic data is that they just wanted to look at the components wise performance of the models as well. So for example, they synthetically created a data set with AR components, and then they wanted to see how does Facebook Prophet works compared to NeuralProphet. And so for those reasons, they came up with synthetic data first and then worked with real world data. So for the synthetic data, they're going to use 5 independently generated time series, which with a daily resolution and 6,000 observations. So let me actually write it down because it's just good to know. So they have 5 time series with 6,000 observations daily. Okay. And then again, these are all randomly generated. When it comes to the trend components, there's only one change point. So before that change point, the trend is upward. After that, it's downward. For seasonality, they're including monthly and yearly seasonality in those 5 time series randomly generated. And then when it comes to events, they're doing 25 random events over this 6,000 days of data, right? So of course it's going to be repeated annually or whatever. So this is the setup for synthetic data, right? And then they're going to compare the performance of the Facebook Prophet, the blue one, versus NeuralProphet, the let's say brown one. Okay. And this is just a reminder of so let's say this is our Facebook Prophet. So Prophet with small little differences, and this is our NeuralProphet. Okay, I use NP for that. Okay, and on the left, what you see is basically the experiments without lag components, right? So they're gonna have a bunch of models, actually let's say, let me tell you what it is. So just ignore this S part. This is synthetic data, and then we have TS. So TS stands for we have trend and seasonality in that data, right? So EF, we have events and future regressors in that. So for example, this has all of them, and this one has trend multiplicative. That's what this M stands for. Multiplicative seasonality. Let's say this one, and then ENF. So this, if you look at that, when we have no lagged component, the performance of Prophet and NeuralProphet should be pretty much the same. And that's exactly the case here, right? So look at that. So they're pretty much the same. And these vertical lines that you're seeing, these are basically the standard errors over different runs, right? So they're using 5-fold time series cross validation, using expanding windows and fixed testing horizon. So this is basically the cross validation. You can go ahead and calculate the standard error of your metric, whatever it is, and then report it, right? So here we're going to use root mean squared error, and which is scaled, root mean squared scaled error. And if you're not familiar with that, so this is nothing fancy. We have our root mean squared error, and we're going to scale it by the performance of our naive forecaster over the training period, right? So this is just basically if this ratio is less than 1, it means that it's outperforming your naive forecaster. If it is greater than, it's not performing as well as that one. Okay, so here I want you to pay attention to the scales too. Look at that. The scales are 0.05, 0.06, and etc. And they're very close to each other. So for the experiments that your time series that you generated has basically no lag components, you will see that the performance of the two models are pretty much the same. This is expected. However, if the experiments include lag components like AR components, then you will see that your neural profit is outperforming your profit in almost all cases, right? So here, we have A and L. So A is the AutoRegressive components, L is just lag values. TSAL, so this is trend, seasonality, AL. We have trend, seasonality, events, let's say future, regressors, and then AutoRegressive. So this has all of them, right? So if your synthetic time series has all the components, you will see that your neural profit is outperforming your profit by a large margin. So look at that. The scale is very larger now. So here is 0.8, 0.6. So there's 0.2 in terms of root mean squared scale error compared to here. This was just 0.01, something like that, right? So yeah, that's at a high level for the synthetic data. I think the model is performing as it should be. This is not surprising at all. I don't want you to think of it as, oh, NeuralProphet is better than Prophet, because it was designed. NeuralProphet was designed to capture something like this. And if you are generating a synthetic data based on these things, so your NeuralProphet better capture that. And if you read the paper, they're going to report the same graphs for components based. So for example, the AR components, or the seasonality components between the two models, which one is capturing what, or which one is better than the other one. But the outcome of this step is pretty straightforward, right? There is nothing surprising here. You expected your neural profit to perform better on this synthetic data that has some lag components, simply because neural profit is designed to capture that. Next, using the synthetic data, the authors go ahead and talk about the performance of the profit versus neural profit over the longer term horizons, right? And what happens if you use more lags, what happens if you use deeper neural networks for the AR components, and what are the findings. And I have gone and summarized all those findings for you here. This is pretty straightforward. Let's look at the forecasting horizon. So we have 1 step ahead, we have 3 steps, and we have 15 steps versus 60 steps. And obviously for we're going to compare the default version of the profit and neural profit first. And this is going to be the performance of the model over the entire test set. So that's why we're not going to specifically report them for 1 step, 3 step, 15 steps, and etc. So this is for the entire test set, right? And we know that both profit and neural profit can do multi-output forecasting at 1 step. So, and as you can see, the default version of both these profit and neural profit models are pretty much performing the same. If I compare their root mean squared scaled error, so it's 4.37 versus 4.41. So as you can see, this is pretty straightforward. And this is not surprising at all, because remember, the default setup for neural profit, the AutoRegressive component is basically switched off. So you expect the profit and neural profit behaves very similarly when it comes to using the default values. And then we're going to say, you know what, let's turn that lag components, AutoRegressive component on and increase the lag numbers and see what are the findings. So that's why we're going to see neural profit for different lag numbers. And as you can see, as the lag numbers increase, the performance is going to get better because the root mean squared scale error is decreasing. So that's one observation. And I think I covered the first one. Profit and neural profit are identical to each other in terms of performance in their default mode. The second one, neural profit forecast improves substantially when configuring any amount of lag. So if these lag numbers is increasing for different forecasting horizons, as you can see, if we are doing 3 steps ahead, it's getting better. 15 step ahead. Of course, using more lag is better, and etc. Right? And this is not surprising that as we increase the forecasting horizons, of course, the performance of the model is going to get worse simply because we are having a harder time to predict 60 steps into the future compared to 1 step into the future, right? So I think everything should make sense here in terms of the table on the left. Now look at the table on the right. So so we said that in general, more lags will lead to better performance. So that's the observation here. So here they're gonna look into the performance of the NeuralProphet using deeper networks, right? So for example, here we have one hidden layer with 32 nodes versus 4 hidden layers with 16 nodes. So as we go down, we are making more lags, going from 30 to 120 and making your network deeper. So this is basically what we have, for example, here, 4 hidden layers with 16 nodes each, right? So, and as you can see, the finding here is that, first of all these neural network configurations are significantly outperforming the linear components, right? So look at the 1 step ahead, for example. Let me see if I can use another color that I have not used. Let's do orange. So for the 1 step ahead, look at these numbers in our scale of 0.5, right? Here, they're very closer to, on average, 0.6, right? So the neural network versions are doing a better job compared to the linear version. So that's number one. And number two, it seems that as we make the network a little deeper, well, this is a little kind of mixed finding, right? So look at that. For a longer horizon, it seems that this is a balanced network, right? So we have only one hidden layer with 32 nodes and 120 lags. And this is outperforming the other combinations in when it comes to 15 steps and 60 steps, right? So the idea is that, okay, so what should we do? Should we always go with more lags and deeper networks? And the answer is obviously no, simply because yes, you might get a little bit of better performance, especially in the longer term, but you're losing interpretability. So if you lose interpretability in the AR component, which is going to be a big chunk of your total forecast in NeuralProphet, then you're going to lose interpretability for the total forecast. Okay. So again, there's always trade-off, and here's always you have to pay attention to what you want to take away from that time series forecasting. So typically, I would say so I think the general verdict, at least for the synthetic data so far, is that NeuralProphet is preferred to Prophet. And of course, you should not use the default values of NeuralProphet. You have to go ahead and specify the AR components and maybe look into more deeper network as well. So we're going to cover all these things in the Python part, but for now, let's just stick to this high-level comparison. So we look at we compared Prophet versus NeuralProphet for synthetic data. Next, we're going to look at some real-world data sets and see how NeuralProphet is performing compared to Facebook Prophet. Okay, so finally, at the end of the paper, the authors are looking at the performance of Facebook Prophet versus NeuralProphet on some real-world data. So I think this was more exciting than the synthetic data, because synthetic data is, I don't want to call it cheating, but there's nothing special coming out of that. NeuralProphet is designed to capture those components better. But for real-world data, this is what I think everybody was excited to see, how these models compare to each other. So they worked with, I think, 16 different data sets, and they categorize it in 4 general categories, right? Human data, economic data, energy data, and environmental data. So, and as you can see, so for example, this is the human data. This is a data set that track behavior or activity of individuals, like tourism. This is our very famous airline passenger data, right? And then we have Peyton Manning, we have birth. Well, the Peyton Manning was the online interaction. We have population trend, which is basically looking at this birth data set. Where else do we have human? I think we should have, yeah, that's pretty much it. Then, and as you can see, the frequency of the data is different, right? It can be monthly, daily, and etc. And of course, the number of observation. This is our airline passenger that we're going to do the Python implementation next time, along with stock price prediction using NeuralProphet in the Python part. But as you can see, there is very few observations for 144, and it can go all the way to data sets with, I don't know, thousands of observations, right? And so again, this is one category. The other one is economic data. So for economic data, we can look at the retail sales. This is monthly data. Or what else? We have this basically energy price, which is hourly more frequently. Of course, we have more observations. So for this one, for example, we can do daily seasonality, weekly, monthly, and etc. But for this one, we can only have quarterly seasonality, monthly seasonality, right? Because the frequency is monthly, or annual seasonality. Yeah. And what else do we have? We have energy data, right? So again, you can just check out the paper, or these are all very famous time series data sets. And I'm glad that they are benchmarking NeuralProphet versus Facebook Profit against all these things. And so this is energy, right? So we have, for example, this represents electricity or power related time series, including demand load, solar and wind generation, and etc. So this is our power, wind, energy. So these are energy. Yeah, we have a bunch of energy related data with different frequencies, as you can see. So we can go as low as 30 minutes frequency. Yeah, even 1 minute frequency, right? So, and then one last category is just environmental data. So I think you can find it here for solar data sets. We have these three. So this captures natural or atmospheric phenomena like solar activity, water levels, air quality, and you name it. But the good thing is that, look at that, we have 16 real world data sets that everybody's excited about, and they're going to compare the performance of NeuralProphet versus Prophet and take the average and report those average numbers, right? So imagine we have a score, which is mean absolute scale error, and then we're going to we can calculate the mean absolute scale error for any of these data sets, and we finally can take an average and report those and compare those, right? So this is what we're going to do on next slide. Okay, so here is the table that we are all waiting for, right? Because this is a real world fair comparison of the performance of the Prophet versus NeuralProphet. And yeah, they're reporting. So let me show you the metric first. They're reporting MAZE, which is mean absolute scaled error. And as you can see, this is nothing fancy. You have your mean absolute error at the top, which is scaled by the performance of your naive forecaster. The predictions are the last observation, right? So this is your naive forecaster, right? So yeah, and if this ratio is greater than 1, this simply means that your model is not good at all. It's not even outperforming the naive forecaster. So, and if it is less than 1, so that's it. That's a good news. So basically it means that it's doing a better job compared to naive forecaster. Okay, so now let's look at the performance for different categories. So starting from the top, so here we have, again, just like the previous table, we have Prophet versus NeuralProphet, and we are looking into infinite step maze. So infinite step simply means that this is the entire test set. So for example, for one data set, if it was airline passenger, your test set, if it is, I don't know, 10% of the data, it's 14 observations, versus another data set that can be thousands of observations, right? So that's why we're using this infinite kind of symbol to show you that, hey, this is the performance of the model in the entire test set. And we know that both Prophet and NeuralProphet are able to basically make those forecasts at one step, right? At once, at one time. Okay. So then again, remember these are going to be the default values of Prophet and NeuralProphet, and you expect the performance to be pretty much similar, and that's the case almost. Look at that. For human, they're pretty much similar, 1.11 versus 1.13. For energy environments, they are pretty similar, right? But for economic data, for whatever reason, the NeuralProphet default setup is outperforming the Prophet. But in general, these numbers are disastrous, right? It's 4.2, 2.3. This means that it's not even able to outperform the naive forecaster. Okay, so if you had nothing but use your previous observation as your best predictor into the future, it would have done a better job. So is it disappointing? On the surface, yes, but the good news is that you could just tune these models, make it more advanced, and that's where it's going to shine, right? So we're going to look at a bunch of the stuff first. So we're going to look at, just like for the synthetic data, we're going to increase the lag numbers and at the same time make the network deeper and see what happens. And these are the findings. So in general, this maze increases with forecasting horizons. So long-term forecasts are naturally harder. So this is not shuttle science. We know that if we go from 1 step to 3 step to 15 step to 60 step, these numbers on average are going to get increased, right? So here, I don't know, let's look at one of them, for example, energy. So here we're talking about the average of 0.5-ish. This is 0.8-ish, then 2, 3, right? So as we go further into the future, it's going to become harder and harder for the model to outperform, right? So that's one observation. Another one is more lags generally improve performance. So we saw something like this for synthetic data, and it seems that for real time series data sets, that's still the case. So here, as we go from top to bottom, we're increasing the lags. We will go from 1 lag to 120. And remember, these are the linear version, and this is the neural network version, right? So as we go from 1 lag to 120, look at these things. Regardless of the time horizons, it seems that on average, the performance is getting better. You see, performance is getting better. And that's the case for 1 step, 3 step, 15 steps, and for all the data categories, right? So for example, for energy, that's the case. We go from 0.83 to 0.46. We go from 1.1 to 0.79 and then 0.76, right? So this seems that this is a general pattern that typically including more lags is going to improve the performance. And remember, you can add as many lag as you wish, so you can go crazy and do 120 lags and then use those sparsify those AR components, right? Just use regularization to just get rid of those irrelevant lags. So you can always do that. And the third observation is deep models outperform linear ones at longer horizons. So if I go to these longer horizons, let's say 60 steps or 15 steps, it seems that the bottom row, which is a neural network, is doing a better job compared to a linear component. Look at that. This is a linear component with 120 lags. This is a 120 lags with neural networks component. And it seems that, yeah, it's doing a better job, you see? But for a shorter term horizons, like 1 step ahead, so for 1 step ahead, let's use Brown. It seems that we didn't need to go with the neural network version. A linear version is outperforming your neural network, right? And that's what we're saying. For 1 step ahead or short horizon forecast, a linear AR model will, with sufficient lags, often works better. So probably, maybe this is a takeaway. Maybe if you're doing 1 step ahead forecast, which I assume most of the time we do 1 step ahead forecast, because if you have the luxury to wait for another day to collect more data to make another forecast for let's say the day after tomorrow, you will do that instead of making a prediction for 2 days now, right? But depending on the task, right? If it is, I don't know, if it is demand forecasting, maybe you're interested to do longer term horizon forecast. But if it is a stock price, no, why would you do that? Probably you're going to create a signal out of 1 step ahead forecast, trade on it, and then tomorrow you wait for the new prices to come, update the model, and then just make a new inference, right? So again, depending on the task and the time series forecasting you're doing, you may end up go with 1 step or multiple step. Okay, but if that's the case, just remember you don't need to think of a deeper neural network, and the linear version is going to do the job as long as you have enough lag, you have included enough lag variables. Okay, so as you can see, there are so many moving parts. In the next Python video, we're gonna play around with all of these things. I'll show you how you can basically to change all these parameters and hyperparameters and look at the performance of the model. Okay, so there's one last slide and we're gonna wrap up this module. All right, so we're gonna end up on this suggestions from the authors of the paper. So you can think of it as a takeaway of someone who has been studying Prophet versus NeuralProphet very deeply, applied to synthetic data, real-world data set, and this is their message to you. Basically, it says that in what scenarios and situations you should use NeuralProphet versus Prophet. And as you can see, most of the time you're going to end up using NeuralProphet. So let's actually talk about a bunch of them and then just wrap it up. They suggest that if your data set is small enough, so probably Prophet is going to outperform. And by small, I mean this is really small time series data set. If you have medium to large data sets, go with NeuralProphet. If you have a long range forecasting horizons, definitely both of them can do good. And remember, you don't need to, if it is something very large, you don't need to do, for example, neural network components. You can do AR components for NeuralProphet. Short to medium range forecast, basically NeuralProphet, they suggest it's better. If you have a specific forecast horizons, they say NeuralProphet is better. So this is, hopefully this makes sense. Imagine you're working with hourly data and you want to predict the, I don't know, temperature 24 hours from now. So this is, I don't know, let's say this is 10 a.m. today, and you want to see what is the temperature tomorrow, 24 hours from now. So 10 a.m. tomorrow. So what is that one? So they say NeuralProphet is going to outperform. And obviously, this is obvious. If there's autocorrelation components, lag regressors, nonlinear dynamics, obviously the NeuralProphet is going to outperform because it's designed to capture that. If you have global modeling of panel data sets, so they recommend that NeuralProphet is going to do a better job. So this is something like, if you have a Walmart store, you have a bunch of stores, and you want to do some sort of global modelings for different products at different stores. Using panel data, probably NeuralProphet is going to outperform. And then this one is interesting though. So if you have frequent retraining on small data sets with constrained computational resources, they say Prophet is better. And I forgot to mention it. It was on the slides, but I noticed that I didn't talk about it. When it comes to training time, so train time, the Facebook Prophet is a lot smaller compared to NeuralProphet because this one has AutoRegressive components, and of course computational is going to be more heavy and it takes a lot more time. But when it comes to prediction and inference, then NeuralProphet is going to be a lot faster than Prophet. So this is time t. Okay, so that's probably why if you have a small data set and with limited computational resources for training purposes, you would do Prophet versus NeuralProphet. And of course, when it comes to prediction, when you require fast predictions, you will go with NeuralProphet. Yeah, that's pretty much it. And I think this turns out to be a lengthy lecture video as well. So I'm going to pause here, and next time we're going to do the Python implementation of NeuralProphet. I put together 2 notebooks for you. One is for basically airline passenger data, which is the most well-behaved data sets that we have been working on through the entire course. And the other one is on the other extreme, right? That's the stock price. So we're going to look into our Apple stock price using daily data and see if NeuralProphet or even Prophet is able to outperform our naive forecaster, and if it is able, by what margin. And that's going to be a good segue to our next course that I'm putting together, which is called Deep Quantitative Trading. So it's going to be a follow-up to this course, and hopefully you're going to enjoy that one as well. All right, so I will talk about the details of that course that I'm cooking right now, but until the next one, take care. I'll see you next time. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.